Resistive broadbanding. If I have a resistor in parallel with a capacitor and I'm driving it from a current source, we can describe the trans impedance gain of this thing, and the DC value would be equal to the resistor, the value of the resistor, so the resistance. Um, if I now reduce the value of the resistor, then the DC gain would reduce, but the pole would also go to a higher frequency. And the nice thing is that the product of the gain and the time constants remains the same. This is the theory behind resistive broadbanding. The second pole can be shifted to a higher frequency, and I want it to have at 1.4, so the square root of root of 2, square root of 2 times the bandwidth, which is 1.4 times the achievable bandwidth. It was already at 1.2 gigahertz, so if I add some resistor in parallel with the load, I shift it to a higher frequency. But already you can imagine if this resistor uh, needs to have a small value, then it is taking a lot of power because it's here at the output. And another option I don't have here, because I must take the non-dominant pole, the dominant pole and shift it to a higher frequency. That is what I can do while maintaining the bandwidth, the product of the poles. So increase the frequency of the pole with with the highest frequency, and that can be done if it is a capacitor by placing a resistor in parallel with it, and if it is an inductor, you place a resistor in series with it. The low frequency loop gain is now reduced. That is basically what you are doing. You are creating less low frequency loop gain. So probably the price is maybe more distortion. And even here we have to drive this resistor. So we need more drive and we have less loop gain, low frequency loop gain. So it might result in more weak nonlinearity. So here I would already say it doesn't sound very as a favorable solution to me. So we can calculate, of course, the result from the fact that we want to shift the the frequency, a very simple thing. We had P2, we want to go to the square root of 2 times the bandwidth. So from this you can find the design equation for RP. And we are going to dual stage resistive broadbanding .pi to show you the result. So dual stage resistive broadbanding. Oh, I have to make it active here. So this one I leave out. And this one I put in and run the whole thing. And you see it's really a perfect way of getting a flat frequency characteristic. But don't forget about the price that we pay for it. So maybe the frequency characteristics look flat. We can also achieve this with the phantom zero, but then the price is much lower. Because look at the value. The value is 70 ohms. We are placing 70 ohms instead in parallel with 100 that we had already there to get this. And we still have the bandwidth also of 1.5 gigahertz. That is here, you see, poles are almost running over a circle if I'm changing this resistor. It is nice to look at this circuit because I want to start with a resistance of infinite, and I cannot put infinite in at the value in slide cap. So then it's better to model the resistor as a conductance and start with zero conductance. And that's what you see me doing because I'm here playing with you. So you see in the variable is GP, is not RP. It is 1 over RP that I'm basically varying. But you see, it is possible to get a little bit less than 1 gigahertz and 45 degrees. So it's really comparable almost with the Phantom Zero if we look at the response, but the price is very high. It costs the double power of the amplifier. So maybe you even have to redesign the output stage to get more current out of it for the same drive voltage. And that would then be then something that is really painful uh, for your total performance of the amplifier. So let's go to HTML result. Do I have it here? No, I don't have it. Here. Oh, it's in Chrome, of course. So, and here, let's go to the circuit. The circuits are all included in the zip file you can download. Yes, so everything is there. And here you see, in parallel with the load, there is a voltage controlled current source, which is controlled by its own voltage, which means which makes it, I can give it the gain 0, and then I have a resistor of infinite. That's, just to start at infinity for the situation without having any effect. And of course, the poles and zeros, blah, blah, blah. The Bode plots, well, we have seen the Bode plots that really can have a nice compensation. The initial calculations are not far off because the effect of the zeros, because of the reduced loop gain, is also less. And because their position is also changed. And then we have pole zero plots, of course, here, the plot that we already have. And you see, you end up with a little bit, well, you can get 1 gigahertz in 45 degrees. That's what you can have instead of 1.4. So there is some reduction, but not as bad as with the other technique. But the price that we pay here is extremely high. We have to double the power of the amplifier. So I think this is not a way that you would like to go to.